Hi everyone, I'm Professor McBain. Welcome back to Chem 100. In this video, we're going to be learning about units and how they help us deal with very large quantities and very small quantities. Hello and welcome to our second lecture for Chem 100. This one is called Big and Small, but it's really about units and how to convert between units. So to supplement this lecture, you should be looking at sections 1.4 and 1.6 in our online textbook, Atoms First. Okay, you don't need to read the heading on temperature units just yet, unless of course you really want to. Yeah, and both of these sections have excellent practice problems at the bottom of the page, and they also have the answers and solutions included. And you really should be trying them out with those provided answers as you learn this material before you go on to your sapling homework and try it for points. Okay. Okay, so here are some numbers that we're pretty good at comprehending, like the fact that it's 88 miles from here to the Sacramento airport, or that a baby might weigh 7 pounds at birth. All of these things seem reasonable to us, at least except the box of Cheerios. That seems a little expensive. But numbers that we're not so good at comprehending tend to be really, really big numbers, like the first one, which is, let's see, we've got a million, a billion, that would be 5,878,625,373,196 miles. I mean, yeah, so like that's a big number, but what we're bad at is comprehending how large that number is. Like, what is the meaning of 1 trillion miles? And this one as well, which is Avogadro's number. We're also not so good at comprehending small numbers, such as these two down here. One of them is the mass of an electron, and the other one is the length in meters of a hydrogen bond length. These are very, 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 very small, and we don't have a really good idea of what they mean. And I mean, also, it's a little bit hefty to just look at this and even figure out what the number itself is. And one of my favorite tweets is actually this one. People don't have a strong intuitive sense of how much bigger 1 billion is than 1 million. 1 million seconds is about 11 days. 1 billion seconds is about 31.5 years. And so this was, of course, tweeted in reference to billionaires such as Jeff Bezos, the owner of Amazon, and many other billionaires who are on their way to become trillionaires in our lifetime, with the commentary that, you know, nobody deserves to be billionaires, or it's unreasonable for one person to, or a few people to have that much wealth. Anyway, let's just talk about how big these numbers are, or how small other numbers like these are. So how can we get a grip on these? Well, the biggest helping hand that we have with this is scientific notation. So scientific notation is basically just utilizing exponents of 10 to help us figure out how large or how small a value is. Okay? So for example, 10 to the first power is just equal to 10. But 10 to the second power is equal to 10 times 10, which is equal to 100, right? So that's what the exponent 2 means, is that you take two tens, multiply them by each other, and that's what that value is. And you can go on and on and on. And if you say 10 to the 12th, then that's 10 tens multiplied by each other. And then that gets you this value, which is 1 with 12 zeros after it, okay? And so you can express this number, which is 5,880,000,000,000 instead as 5.88 times 10 to the 12th. And then that really means this, okay? So instead of giving that really, really long value, you can instead express 1 light year as 5.88 times 10 to the 12 miles, okay? And so the way that you can think about it, let me get my laser pointer. The way that you can think about it really is this number, if you instead start one place to the right of the very first number in the sequence, okay, so then you would write this as 5.88, okay, And so then what you do is you say, okay, well, my decimal is over here. Let me look at how many times I need to move the decimal point over in order to have this be the number that I put in front, which is kind of a funky way of thinking about it, okay? But just bear with me here. So the decimal point is really here. Now I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times, all right, in order to get from 5,880,000,000,000 to 5.88. Okay? And so then having moved that decimal number that many times, that tells you the exponential value that you're going to assign to the 10 that you multiply 5.88 by. Okay? If you don't believe me, why don't you type this into your calculator right now? And then you should see that this 5.88 times 10 to the 12, it should come out as this. And so then that tells you that they are equivalent. Okay, so that's all well and good to see with an example, but why don't you take a turn, okay? And so anytime that you do a conversion like this from like the real value to the scientific notation version of that number, you'll always want your answer to have just one digit to the left of the decimal point, okay? So why don't we start with this number right here, okay? So if the decimal starts out right here, how many times do you got to move it in order for it to end up here, right? Which is exactly what we were talking about. The digit needs to be, there needs to be just one digit to the left of the decimal. Okay, so however many times you need to do that, well, then that's going to be the number that you assign as the exponent of 10 that you're going to multiply this by, right? Kind of, sort of. Give it a shot. I'll wait. All right, let's see how you did. So for that first number on the top, you should have written 6.02214 times 10 to the 23rd. And then for the second number, you should have gotten 7.92 times 10 to the 10th dollars. Right, so notice again that I followed the rule that I mentioned where we end with just one digit to the left of the decimal, where we end up putting it, right? And then again, I'm focusing on how many times I moved that decimal, okay? So you might have heard like, oh, it's how many zeros that you have, but really it's more like how many times you moved the decimal in order to get this as the we call this the coefficient of your answer, okay? Okay, so we can also use scientific notation to communicate small numbers very quickly, okay? So this is where we're getting into the negative exponents, okay? So anytime that you see a negative exponent, that means that it's a small number and it's definitely smaller than 1, okay? Whereas the positive exponents are larger numbers, much larger than 1, okay? So the 1 starts telling you how many times you've divided the number 1 by 10, okay? So for example, 10 to the minus 1 is equal to 1 divided by 10, and that's equal to 0.1, okay? But then 10 to the negative 2 is equal to 1 divided by 2 10s multiplied by each other. You got it? See how there's 2 10s there? You can also think of it as how many times you had to move the decimal spot from right here in front of the number 1 to the left. Okay, so if I move it to the left once, then I get 0.1. If I move it to the left twice, then I get 0.01, and so on and so forth. So 10 to the minus 11th, yes, you're going to have 10 zeros after the decimal, but I really don't like that way of remembering. But I really don't like that way of remembering the zeros rule. It's much better to remember that to get from here to here, you had to move the decimal point 11 times. So if you start here, you would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So this will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like that. Okay. Right, so for example, if you were given this value here and I asked you to convert it into scientific notation, then you would say, okay, well, if this is where I'm starting and I want to end up with my decimal right here, right? That's the rule that we discussed on the previous slide, where your final answer has just one digit to the left of the decimal point. So I'm going to go here and I'm going to be like, okay, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so my final answer would be 7.414 times 10 to the minus 11. And then, of course, it's got units of meters, which we'll talk about in a moment. So again, it's 7.414 with the decimal moved left 11 times. All right, so here's some more practice problems for you. Try that one. And try that one. Okay, let's see how you did. Right, so this is, probably took you a while for this one. So this is 9.10939 times 10 to the minus 31. And the units are kilograms. That is actually the mass of an electron. It's very, very small. And then the other one is a little bit quicker, hopefully. So that's 8.8 times 10 to the minus 13th. That's the volume of an E. coli bacterium. There's our bacterium. Okay, so why do we even care about things that are small and things that are big? Well, because this is a pretty big problem with chemistry. A lot of the things that we're discussing are very, 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 very small, such that we need to utilize these very, very small exponents, these negative exponents, in order to describe them, okay? And then other things are too big, and these tend to be the quantities of those very small things, okay? If you have a lot of very small things, then of course you're going to have numbers that are in the very large positive exponents of that material. So to help us deal with these big and small quantities, one of the nice things that we can do is to convert from the English system, or really the American system, into the metric system. Okay, so in the metric system, length is described with meters as the base unit. This is Dr. Chris Nichols' daughter. I think this is Piper as of 2012. And then, let's see, the unit of mass is a gram, and 1 gram is about 1 or maybe 2 M&Ms, all right? So the gram unit is actually a pretty small amount of mass, much, much smaller than a pound, for example. And then a liter is about a medium or a large sized soda, okay? And this is volume, okay? So we've got length is meters, mass is grams, and volume is liters. And so one of the things that we do in the metric system to get larger and smaller quantities is, instead of coming up with a whole different unit, all that we do is we keep adding prefixes to the base metric unit. So if we are discussing a very large amount of something, then instead we just pop the kilo in front of that thing, all right? And so a kilo of anything is 1,000 times the base unit. So for example, if you have 1,000 grams of something, then you have a kilogram, right? And so then similarly, the mega is 1 million of that thing, and then the giga is 1 billion of that thing. All right, so then the smaller ones are centi, milli, micro, and nano, okay? And there's a couple different ways that you can get a grip on the smaller units. I prefer the way that's described here in bold, okay? So the centi is smaller than the base unit, and you need 100 centimeters in order to equal 1 meter. The other way you can think about this is that the centi is 100 times smaller than the meter, right? That makes sense. But I prefer this way, where I think of how many of the little guy I need in order to equal the base unit again, all right? So then similarly, a milli is 1,000 of that thing. The micro is 1 million of that thing. I'm sorry. So then similarly, the milli, you need 1,000 millimeters to equal 1 meter. Micro, you need 1 million micros to equal that thing. And then you need 1 billion nanos to equal that thing. Okay. There are also other prefixes, but they're not going to be used as often as these that I've got here above. Okay, so these are the 7 prefixes that you should be at least trying to familiarize yourself with for this class. But the ones that you'll need, say in an exam setting, they'll always be provided for you in your useful information sheet. That's also provided for you at the very back of the book. All right, so that's really all that you need to know about the metric system at this time. Now it would be a good idea to hop over to the video on more exercises with the metric units, and we're going to be talking about some ways to convert between these units. Okay. Don't forget also to look at part 2 of this lecture video.